There we go. Right course, right place. Cool. All right. So I'm assuming someplace when you guys had fluids with Haskins, he told you some things about pumps.
Why are you talking to them?
I know why I'm talking to them because they started out in there. He's the only one I know that really hasn't had any fluids, and you're the only one in the room that's actually, well, besides me, that's graduated with fluids.
I don't even know how I did.
I don't know how you did either, but you
I'm
did.
right.
And the funny part was, I was told if a couple of you stayed in, you might have just made it.
That was me. Like I got 2 really good grades on the exams, and then I got 55, and I just kind of maintained that C. Got a good grade on the final. Did all the homeworks.
I was thinking reality.
Best worst case scenario.
I need to play lacrosse.
Yeah.
I need to put it across. Education, lacrosse. Education, lacrosse. What was your excuse, Cameron?
I don't know. I didn't think I was going to pass it either way.
I do believe you're one of the ones that would have just made it.
I wasn't making it.
No, I think you were probably not making it.
No, I wasn't making it.
But I also think it comes down to did you get over to accommodative services and talk to them?
No, I never, because the semester was up. I gotta do the thing again.
Do it.
Hello.
Because that's
Okay.
disabilities are okay.
Yeah.
Don't accept that fact that you gotta struggle with it. Anyways, so completely off topic, but let's get back on topic. So circulators. So given the fact that Fitzsimmons here is the only one that actually understands what a pump looks like, we're gonna go over the basics of a pump, and then we're gonna go into a little more of why I told you where the circulators fit in the system. And I'm gonna do it from a PS pressure drop diagram so you can see what happens with it. So the right way, the wrong way, and then we'll go from there. Okay. And then that'll get us to Monday. We'll start taking a look at different circulators and their pump curves, how to pick pumps.
We didn't really mess with circulators and
He
fluids.
tends to never get there.
We didn't, like, I think we, like, he mentioned it in a system, but the only thing we actually did work on and calculated were pumps. Up from, like, a reservoir up to.
Yeah. So I'm going to take you the rest of the way. But years ago when I taught the fluids course, we got through all this. And all right. So anyway, so how this works. We have an inlet. We want this to be, oh, I didn't put you in the background, did I? Okay, let's do this. Set pictures background. Okay, so now I can be able to write on this. So we're going to have suction pressure here. Okay, and we're going to have discharge up here. Okay, the pump does not make pressure. Keep that running through your head as you're doing this. What makes the pressure is the system. Okay, piping, all that sort of stuff. People get really hung up with, well, a pump makes pressure. Well, we look at pumps in terms of pressure, pressure head, friction, all that sort of stuff. It's not the pump making the pressure, it's the rest of the system. The pump is only capable of doing what it can do inside the system. Okay. All it really does is make flow. But we have some basics to this. So we got, this is the impeller down here. Fluid comes into this point, which is this eye of the impeller here, and it gets spun out of the vanes. Okay, so the impeller is this whole disc, and that fluid is going to hit that and get spun out. And if you look, it's not quite in the center of the pump housing. Okay? It's offset a little bit. Okay? And this whole, well, they call it a volute. This whole thing is called an involute, which is the housing that's there. But if you look here, water comes into the center here, squeezes out into this vein. As this vein here then rotates this way, we're increasing the amount of space that we can throw that water around. Okay? But it's always based on that little small first opening in the veins. That's what's moving. But then as we give it a chance to start getting some motion to it, we open up the housing and we give it a chance to flow out. Okay? The other thing is this: if this was not tight right here, we would have this fluid going in there and try to bypass going out the discharge. All right, that happens. Fans do it notoriously. Pumps not so much, but fans will do it. Air's less dense than the water. With a pump, it'll try to shove it where it wants to go, but it will seep into the veins again. A fan, and we'll talk about fan curves in another couple weeks, but the fan, if it doesn't have a choke down point, it will drive that air back into the rotation of the fan blades, and then it'll start freewheeling. Because we got all this air in motion, it actually takes over the pump, or takes over the electric motor and starts going down, and we wind up overheating the motor. So you want to be careful of that. Pumps are a little more forgiving, but not as not completely. Okay. All right. So we got the impeller. That's the thing with the disc. We got the flanges. These flanges here don't have to come with the valve shut off sound, but it'd be nice if they did. And they do sell them that way. I wouldn't ever spec a circulator that doesn't come with its valves attached, because you're going to put them in anyways. So why not just have them bought that way? Any questions on what it looks like on the inside? So when you guys get the fluids next fall, you'll be good. What's that? Oh, you're doing it? Oh, are you? Oh.
Yeah, we are.
Is that a thing?
It's a thing.
It's gonna be.
I wish I would have known that.
Dr. Craig
It's gonna be a class.
will do it. Okay, so there are two types. This one's a wet rotor, and this one they call a three-piece.
Is that a take-o on the top there?
It is. Okay.
I'm Chico certified.
Dude, I'm sure.
I am.
You're
That's
certified.
from BOCES. Not taken. Oh,
At least it's not calling it taco.
Is it fun?
All right. For our residential systems, we like the wet rotors. They're small, they're compact, they do the job. When you get to commercial systems, you're going to need to go to a larger pump. Okay. So it winds up being one, and it's three pieces because here's the motor. Here's the bearings and seals. Okay. And then here's the involute. Okay. And that's the three pieces. Okay. Those don't usually come with the ball valves on both sides. You have to design those in. And trust me, on a commercial system, you definitely want to design a lot more bigger valves. It's also, these are the ones I showed you down in the lab, the boiler room the other day. Always put them in pairs. There's going to be one that goes bad. Okay. Now, the downside of that is it's money you're spending. And if you can get a pump in a couple hours, I would never put on two. to get a pump of this size, I can't just go to Syracuse and get it. It'll take a day to get it up here. So it'd be nice to have a spare. If I'm in Syracuse and I have a pump supplier right there, and I know they got one in stock, I can just go get it when I need it. Okay, so it'll save you money on the job. But from a design standpoint, design it with two. Had a friend of mine who's an engineer over in Vermont. He built a new building, and he argued with the design firm that I don't want a second pump. Well, but you should. No, I can. And where he was, you go to Randolph, the capital of Vermont, Rutland. You can go to Rutland in an hour and pick one up. So he's like, I'm not wasting money on a second pump, so we're gonna put one in.
Castleton.
I only know one city that has
Castleton.
it's Burlington. I know like
Castleton.
Okay. So, anyways, from a design standpoint, cost is money. All right. So here's the inside of a wet rotor, and because this is the one we're going to play with the most, that's what I'm going to do. The 3-piece pumps, they're pretty, you can't fix anything. They got to go back, and you got to get a new one. But with the wet rotor, we got a junction box over here. That's all the wires are tied into. These operate at 120 volts, and I think they run about 8 amps in their operation. We got the inlet, we got the outlet, or vice versa, depending which way you want to see them. We still have an involute here. We get the flanges, and there is a big rubber seal that goes right in through there. That God help you if you don't have it. You can bolt 2 flanges together, but it will leak. Okay. So don't lose the seals when they come with them, or the bolts. Okay. Some of the bottom half of the flanges are threaded, which is the best option. The others are what's the word I'm looking for? You don't solder onto these. What's the word I'm looking for? Threaded pipe. ProPress. Sorry. They have a ProPress fitting on the bottom of it. Okay. They do make them that way now. Usually it's when the valve body comes with it. You can ProPress them. Okay. So there'll be an extension of copper pipe out there. The important part of this is everything inside this motor housing through here is wet. So there's a ceramic housing that goes around the windings to keep the electricity from getting in contact with the water, because that would be a bad thing. The good news is it's that fluid that you're pumping through the system that provides the lubricant to keep that ceramic stator. No, stator's the outside. No, the windings are outside. Stator is the centerpiece. Keeps that floating in the center of the electric windings. Okay. And with that, you basically cause a nice lubrication. The downside to wet pumps, when they go bad, they go bad. Okay. Cool thing is I can replace the pieces. I can literally take all of the bolts off here and take all this out. Leave all that still attached, and I can buy new parts for the center. I'll say this nicely. People that are doing that is because they're desperate. It's easier to go buy a new pump. Okay. Are they repairable? Yeah. But time and labor, just go buy a new pump. Takeo 007s are everywhere. Hell, even Lowe's stocks them. Okay. So it wouldn't be worth taking that repair out. But the trick is when they don't run long, they tend to seize up. And it's not because there's anything wrong with the impeller. It's the fact that this has been sitting there without any fluid running around it, and it's settled on the bottom of the ceramic housing. And it won't start. So when you go to test one of these, you put an probe on and you measure the amperage drop. If it's high amperage, I guarantee you the thing's stuck. Okay? Now, gentle persuasion from a hammer may cause it to move. But if you do it once, you're going to do it a lot, and you're going to have to go eventually replace it anyways. But if you're in a desperate point of action trying to get this thing to work, yeah, a little gentle persuasion will get it going. Then don't shut it off until you get a new pump. Okay? But we tend to, why I know this so much is all our circulators come out of the systems around here, and we set them in the shelf, and they don't get any lubricant around them. And it's a matter of, we should just seal them up with some water in them so that they don't, but we don't have ball valves on our pump, so we're kind of stuck. We eventually throw them out. Okay. Any question on what the inside of this thing looks like? All right. How to install them. Okay. Pay attention. Up is in this direction. We have a pump coming off here. Here's our circular or expansion tank. Here's a circulator. There's a circulator. And by the way, Tacos come in different colors. So I've seen them tan, green, and black.
Me too.
What's that?
Me too.
Yeah. It doesn't matter. It's just whatever paint job they had at the factory the day they put them together. And sometimes part of it's age. But anyways, so remember what I did up here with this whole inside housing had to have some fluid around it. Okay. So get out of there. If I come back to this one and I look here, these are hanging down. Problem with hanging down is all the water settling all around it. First thing, that's bad. Second bit is if I turned it up the other way and had them up instead of down, none of the water gets into the lubrication of the pump. So they're always hung horizontally. Okay. Question? No? So literally on this particular pump, I would do this. Here's my pipe. Okay, what's the matter with you?
I think it's because you're locked on.
Here's my pipe. And I got water flowing through there. I'm going to hang that thing sideways at all costs. Okay. So this is make it parallel to the floor. What's that in?
Can you hang them vertically or no? Can you do them vertically or no?
Yeah, as long as the motor housing stays parallel to the floor. There's no harm in going up and down, but I can't. Vertically is okay because I can go anywhere 360 degrees as long as it's perpendicular to the pipe and parallel to the floor.
Right.
But it's always, it gets stuck in someplace, and someone went, well, I'm going to hang it from the bottom because I need clearance to do something else. Can't. Yeah, I think I got another picture here I stole from Siegenthaler that talks about that. But you can't have them hanging up or down. Horizontal. That's all there is to it. Okay. All right. So this one I got more for a picture of how to properly hang all this stuff. Okay. So I like this picture. I liked it from the standpoint of how to fasten all this stuff together, not from the locations that John put in the picture. What did I tell you about where do you put the pump in the expansion tank? You want the pump after the expansion tank.
Yeah.
Okay.
Expansion tank goes first.
Yes. So it is correct in the point that the expansion tank's here, the air scoop's there. But I literally got 3 pumps after all that. Okay. So if I was going to do this kind of scenario here, I would have made this one a pump here and made a primary loop that came back around. Okay. So that I'm taking care of the primary loop. Because right now, each of these pumps are going to pull pressure out of this, but each one's going to fight the other. Maybe you don't. Well, I know what I said, but I don't know if I said it correctly enough for you to see it. So let's say the first circulator comes out. It's going to supply to its zones. It's going to have a pressure loss of something, right? The next pump's going to get the same pressure. It's going to provide its, but each little piece down the way, first one is a truly 12 psi. The next one is a few little less than 12 psi. And the next one's 2 parts less than 12 psi. So really, by the time you get to the fourth circulator, is it really the 12 psi you started with? Because you got the friction loss in that loop. Okay? And then the other bit is, let's say 1, 2, and 3 don't actually call it, 4 does. Now 4 is pulling all the fluid there. It's the first one on call now, and the next one comes in and says, let's take number 1. So 4 was calling, 1's right closest. Water will always go to the shortest distance possible. So that means 1's getting all the pressure, and 4 is going to starve itself a little bit. Okay. There's some problem there. That's the other reason why we have primary loops. So in a primary loop, we got a circulator that's moving it around that whole loop all the time. And then the zone pumps are only pulling what they need. Okay. So that's the advantage of a primary loop, secondary loop. But what I really wanted this picture for was not this stuff. I wanted to talk about, make sure you hang things, and if you can't hang it, you put the bolt this thing to the wall. Okay. Put a metal strap on there and strap the thing to the wall. Nothing on this thing should ever hang free in space. Okay. And by the way, that's a good thing to get you through a lot of things, even electrical situations. So jump, my house well pump cannot be fastened to the wall because it's a stone wall and the mortar's too weak to actually grip on anything, and the stone's too hard to drill. So literally I have a ceiling to floor board, and I fasten the bottom of the board to the concrete below and up to the floor joists above. And that's how I actually anchor the electrical wiring to my well pump. Is I have to have something down below and I can't get into the wall. But you're gonna have to have something. So you're gonna have to make it come up with parts and pieces to make it secure. Because this stuff dangling in space is not a good thing. Okay. So anyways, as long as we're back to John's little system here. If you had to expand things, let's say you got 4 zones and you're going to add an addition to the building, the nice thing about being capped at the end is I can pick that up and carry on. If it was a primary loop, let's say I did actually come back in here, I would just change this out, or if I was planning ahead for stuff, I would make this a T. And then I could add on to it, but then I'd have a valve right here. That's not a valve. I would put a valve. Okay, let's not erase everything. I would put a valve right in here that I could close. Okay, and then I can add on to it. So if you're designing things and you know the customer is going to ask for something more, build it in there, okay? And it won't cost you much. I mean, talking $20 for a valve and another $20 for some T's, okay? And you're that much further ahead in the process. You can allow for expansion, okay? Now, it doesn't mean that the boiler can handle the expansion, but you can at least design your system so you can add to it, okay? Note on that, we're good. Where are we here? Okay. We're going to get into the fun stuff now. All right. So here's the system. And ideally, I want to draw it not like you'd seen before. So we're going to start here. We're going to go over. We're going to have an expansion tank. We're going to come over. We're going to add the pump. We're going to come off the pump. We're going down. We're going to hit a 90-degree L. We're going to overhit another 90-degree L. We're going over and hit the third one. 1, 2, 3, 4. Yep. And then we're going over and hit the last one. And then we're coming back to there. It's not really all that piping. It's just that all this comes back to, actually, I know how I want to do this. Cool. We're going to do this. Out of here, A, back to here, A. Okay. So come back around to where we started. But it's really a three-dimensional loop. But I want to be able to draw a diagram with this so you can see what's happening. So here's where we're going to go. We're going to start out here at 10 psi. Okay, just to say that the expansion tank has 10. Okay. The distance from the expansion tank to the inlet is going to be 9 psi. Okay. The discharge is going to be 18 psi. Okay. And then our first elbow here will be 17 psi. The second one will be 15 psi. The third one will be 13. And then the last one will be 11. Yeah. And then we're going to come back to the 10 back here at the beginning. Okay. So far, so good. Okay. This is the diagram that's really important with all this. Okay. So we got a system, ideally. It's going to start right here at the here. And we're going to go this way. This will be, which line do I want to use here? I want to do, this will be 0 psi. Okay. And if I take a look at this whole system, where'd my markers go? Draw. Cool. Sorry for making you dizzy, but I'm looking for, there we go. We're going to have So if we turn the pump off, circulator in this particular case, we'll stabilize the pressure inside the system. And a good visual for you guys to think of that as what it is. Remember in refrigeration 1 when you turned on the Scott trainer before you turned it on, both sides high and low were 80 psi? Maybe. Okay. So the refrigerant in the system will find an equal balance of its operating system. As soon as we turn it on, the Scott trainer will take the 134 refrigerant and drive it up to 110, 125. I like 135 out of it, but it's not getting there lately. But it'll drive it up in the hundreds for the high side pressure. And the low side pressure drops to about 42. Okay. So when you turn off all your circulators, everything in the system will just balance out because it's just going to drift back through things. Okay. Make sense? Okay. So really, the boiler is the place where it does all that because it's got no corms passing fluid backwards. Okay. As long as the circulator's off, we're going to get a baseline of 10. Okay. But I gave you the pressures up here, so we're starting at 10. Okay. Let me do this in. Let's do it in green. Yeah, we'll do it in green. Okay. So we're starting at 10 here. We're going to go down to 9 here, and that's 9. We're going over on the discharge up to 18, and I may not have left enough room in here, but we're going to go up here to 18. Then we're going down to 17. Okay. Then we're going down to, let's put that where it belongs. We're going down to 17, down to 15, down to 13, down to 11, and then back to 10. Okay. So literally our curve for this looks like this. We're up, we're over, we're over, we're over, and we're over. Okay. That's called your what I'm looking for here. That's your system energy. Okay. So how much energy is in there to make fluids flow? All right. Normally, and Ian, I know Haskins never gets into this. But it's not so much that I want you to memorize how to do this, it's that I want you to memorize what it looks like when you're thinking about a system. You're going to look for things that the pressures aren't right on. How's the system supposed to perform? So the only thing that actually increases the pressure is the expansion tank and the pump in combination. Okay? And when things go, every time you go someplace, it's going to drop. I didn't put any fin tube in this, I didn't put anything else in it. Literally all that gets accounted for. Okay. Now let's do one where the circulator is on the wrong side of the pump, or the pump's on the wrong side of the circulator. And I'll give myself a wee bit more room this time. Still got 0. Okay. But now what we're going to do, I should draw this out again. So circulator first, going over to the expansion tank, going over to that elbow, 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 and then back. So A back to A. So a closed loop system, okay? All right, so stop it. Get out of there. We're going to start here pretty much at 11 psi, okay? Then we're going to the expansion tank, and that's going to be no pressure change. Okay, so that stays at 11. Okay, first one's now going to drop to 9, 7, 5, 3, and then believe it or not, when I come back around to the pump again, I'm actually going to be starting right here at a -2. Okay, so this curve, when you look at this one, is going to do this. It's got a spike up, it's going over, down, 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 and then down into here underneath the line. Okay, and that's what happens when the pump is ahead of the expansion tank. And it's because we didn't add enough pressure head to it to begin with. Okay? As we literally allowed the pump to push everything it had into the expansion tank, but the expansion tank doesn't give it a boost. Okay? That reminds me. So I did just use the word boost. In true fluid mechanics, an expansion tank is a accumulator. When the pump can't produce the flow rate it needs, the accumulator has fluid stored in it and will push it forward to make up the difference. Okay? But in this case, because it's a closed system, it can't, because there is no space for it to add any more fluid. With me for following that logic? Okay. So we got a fixed volume in there. We can't change that. But if I have an accumulator where I actually can store extra fluid and I have it under a high enough pressure, when that pressure is needed and the pump can't do it, the accumulator can add to it. Okay, so it's an additive process. Okay, expansion tank is that storage device we use to keep it from going over pressure, but it also adds pressure to it because we already put, say, 10 pounds of air in the bottom of it and it's pushing upward and all that sort of stuff. Okay, so it works on the same similar principle, but not exactly in the same format. Okay, but what happens is I'm also getting the pump. The pump has, black please. Pump has so basically the cavitation issue is this. When a pump sucks fluid in, it's lowering the pressure, but if you get the pressure low enough, any air that's trapped in that water will come out. Okay? When it does, it explodes. And I don't mean it goes boom, it just goes pop. But every pop is going to wear that little air bubble, is going to wear out part of that involute and make problems for your pump. On wet rotor pumps, what it does is it wears out the vanes, and that's usually what goes wrong. Okay, so if you get there and you take a pump apart, you see that there's half a fin missing. It's not on just one, on all of them. It's because something blew up in there and broke that plastic vane apart. So that would tell you that you got to go look for something else in the system that's wrong. So it's a good troubleshooting skill when you're trying to figure out why things don't work. Okay. All right, so that's what a system curve really looks like from a pressure drops across things. If you go back and read Siegenthaler's book, chapter 7, he'll explain it, but he does it three-dimensionally, which is a great image, but not easy to draw. Okay? This should just give you an idea when you're looking at things. You already know all the pressure drops. We did that last semester with friction losses. Okay, so instead of PSI, you can do it in terms of head too. So if I have a 0.02 drop in head because of this valve, and I have this distance of pipe, and it's this loss of head, you can plot the same thing. Okay. You good, Dylan?
I think so.
All right, we're gonna stop there. Like I said on Monday, we'll get into pump curves and how to choose the pump based on systems.